Hello and welcome again to my Physics Online video series. Today's video lecture we're going to be talking briefly about the electric field. Since most of you who are watching this are fairly new to physics, mathematics, etc., I am not going to simply define the electric field right off the bat. Instead, I'm going to give you a very simple definition of what a vector field is, and then relate the electric field to that. So vector fields in general essentially consist of a series of sort of instructions for different points in space, wherein each point has a value associated with it, and that point may have a large value or it may have a small value. It also has a direction. So essentially you have a vector that is associated with each point in space. And the vectors may be the same or they may be different. They may be a function of something like your coordinate system, etc. So that is a general description of a vector field. So for example, maybe you want to have a vector field to map out for an object how much force is going to be applied to the object from gravity. So you've got a planet somewhere, let's say right here, and now you have an object, and you place the object right here. Well, if the object happens to be right here, then maybe we represent the force of gravity with this line. If we take that same object and move it to right here, then the force of gravity should still be directed towards the planet, but since it's farther away, you have a weaker force of gravity. So now your force of gravity might look like this. Maybe somewhere else in the orbit, you happen to be fairly close into the planet like this. So same object again. And the force of gravity now maybe looks like this. So this would be Fg at this point, this would be Fg at this point, and this would be Fg at this point. So if we took the collection of all possible points in the space around this planet, and we mapped out how much gravity would be pointing towards the planet for this other object, that would be a sort of vector field. In fact, we actually would probably modify it because this is very particular to this one object. I could instead have another object. Let's say I replaced this asteroid with maybe a slightly bigger asteroid like this. Well, then my force of gravity will be correspondingly larger for this bigger asteroid being located at different locations in space. So what we might do in this case is, instead of trying to figure out what is the actual force of gravity for this particular object, is we might say how much force of gravity is there per unit mass. And so if you go back to free fall acceleration and to stuff near planet Earth, so here's the Earth, and you're close enough to it that you're basically 50 feet above the ground, 100 feet above the ground, that kind of thing. Then the force of gravity that acts on our object, no matter how high up it is, always looks like m times g. Here it is again, m times g, m times g. Little g is actually what we would call the gravity field strength. And so if we go back to this idea of you have a planet and now you're looking somewhere out in space at the planet, your little g would always point towards the planet. It would always have some particular value, and that value gets larger as you get closer to the planet. Okay, so here's a little g out here. Here's a little g a little bit closer in, and then here's maybe little g as you get very close to the planet. And we basically can just draw this set all around the planet and then associate with it a set of little g values locally. And so eventually we end up with something that looks like this. And I'm not going to draw the whole thing on video because it'll take a little time. So this entire drawing that I've now made is a simple representation of what the gravity field strength is everywhere around this massive object. In fact, this gravity field, let's make this a capital M since it's a big mass. This gravity field, little g, would look like the universal gravitational constant, big G, times the mass of the object that's producing it, divided by the square of the distance between the object and the location that you're looking at. You might throw a minus sign in here since it points inward. Okay, so that's a gravity field. That's a type of vector field. And if I now have another object that has a known mass and I place it at one of these points, or any point, then multiplying that mass times this little g gravity field gets me the force of gravity. And then when you're near the surface of the Earth, little g ends up being approximately 9.8, although in these units we would say newtons per kilogram rather than meters per second squared. So the electric field works in a very similar manner. Instead of a massive object, I have a charged object. So I'll say plus. Maybe this has a charge of plus Q. And I want to know if I have another object that has a different amount of charge, or maybe the same charge. We'll say QT for test. How much force is being applied to that test charge? Well, we know that the answer is dependent on how much charge is present in the test charge and also how far apart the two of them are. So if this distance right here represents distance r between the two of them, then the force, Coulombic force, would be Kc Q times Q test divided by r squared. All right. But that gets us only the force for this particular charge at this particular location. What the electric field does is it says, let's take a collection of different points near our source charge and ask for each of these points how much force would be applied and in which direction for this particular charge. And then we step up one step further and say, instead of using this particular charge, this test charge, how much would it be for any charge at all? Well, to answer the first question, we can still use this equation. Fc is kq qt over r squared. Now, to get for any charge at all, we need to divide out this charge and multiply by whatever charge we're using. So maybe for a generic charge, we would use Fc is Kc Q Qt over r squared divided by Qt and times Q generic. And so that would get you the force on your generic charge, and so on. But in doing this, it should be evident that you have kind of added some extra steps, because I can eliminate this and this when I do the division, and now I'm just multiplying by this thing instead. But if I wanted to get some other charge, I'd multiply by that other charge instead. And so it occurs to me and to anybody who's paying attention as they watch that if I take this element here and multiply by the charge present, then what I have is the total force acting on that charge. But we might as well just isolate that one element and call that the electric field. So this actually gives the expression for the Coulombic electric field. Now that we've done all this, let's write a better definition for what electric field is doing. It basically is giving you how much force do you have per unit charge at any region in space. Okay, so this is anywhere in space near a source charge. That also means, for what it's worth, that if you know what the electric field strength is and you want to find out how much force is acting upon an object, then you take the electric field and you multiply by the charge. Okay, so that is essentially your definition and fundamental use of it. The Coulombic electric field, so we could call it Coulombic electric field, is what we found on the previous page. So we could say like E Coulombic is the Coulomb's constant Kc times the charge source, we'll call that the source charge, divided by r squared, where r is the distance away from that source charge. Okay, so there's been a little bit of a bait and switch in as much as this is now the source charge, and so this right here should be called source charge. This one right here is also source charge. Okay, and that is basically electric fields. Now you can find the electric field for multiple source charges by using what's called superposition principle. So if I happen to have, let's say, Q1 source here, and I have another Q2 source here, and I want to know what is the electric field at this location doing, what I have to do is figure out what the electric field due to number 1 is. I have to figure out what the electric field due to number 2 is, and then I basically just add the two together to get my total electric field. So this would be the total electric field at that location. E is E1 plus E2. And I can do that for more than two charges as well. Actually, working an example like that would be a bit much for a short video, however. The basic procedure here is to essentially determine magnitude and direction of the field from E1 and E2. So determine magnitude and direction of E1, E2 using Coulomb's law. Then step 2, break into Cartesian coordinates. You do that by using the magnitude and directions. Basically, how strong is the E field and what angle is it at relative to, say, the positive x-axis. Then you add the x's together, and that's your total x. You add the y's together, that's your total y. And then last step, you would maybe convert back to polar. So recombine into a total magnitude and total direction. So that is the basic procedure for adding multiples. One kind of tip to it, it's best if you measure your angles as being counterclockwise from the positive x direction. And the reason why is because then if you've done that, if this is theta 1 and this right here goes with E1, then E1x will be E1 cosine theta 1 and E1y will be E1 sine theta 1. And the same will work for E2. So that's it.